Okay, today is our inaugural lecture in chemistry. We will be talking about these concepts in video so that you can spend your time in class, or we can spend our time in class working on the various problems that come up when you work your problems, or concentrating on areas that are more difficult to understand. I want to thank Christy Cochran's mom for suggesting this. I think it's an excellent idea and a way to maximize my time with you in addition to our help sessions that we have. Today is the third lecture of the quarter, and this lecture is on electrochemistry. Electrochemistry uses chemical reactions in order to produce electricity. And this electricity is then used to power various situations. This is an example of an electrical vehicle that contains a very large battery pack. And we'll talk quite a bit about the various types of batteries. And these batteries produce electrical energy by means of a chemical reaction, and they power a motor that converts that electrical energy into kinetic energy, and the car moves. Now what you see here is these batteries, which we will show are called secondary batteries. These batteries can be recharged, and that's very important, obviously, since they're large battery packs, very expensive, and if you had to change them out every so often, that would be very inconvenient. Now, electricity can produce various phenomena, and I'm just showing this because this is a chemistry class. We haven't talked about this before in this class, but it can produce phenomena such as lightning, static electricity, which is what's causing this girl's hair to stand up, but then it can also produce a current by a battery. Now, the fundamental part of the chemical reaction that causes the formation of electrical energy is called a galvanic cell, and this galvanic cell takes advantage of something known as an oxidation-reduction reaction. The first section of this chapter, which we did not go over because we discussed the balancing of oxidation-reduction reactions in the previous lectures several weeks ago, goes through how oxidation and reduction occurs and how to balance these reactions. So a galvanic cell, also called a voltaic cell, is a device where a spontaneous oxidation-reduction reaction, which I generally call a redox reaction, produces electricity. The site of oxidation, the pole that has a negative charge, is called the anode. The site of reduction, the positive pole of the battery or galvanic cell, is called the cathode. This diagram shows that if you put a clean piece of copper into a clear solution that contains silver nitrate, oxidation reduction occurs between the copper ions and the silver ions, and as the reaction proceeds, the solution turns blue because the copper ions are being produced, and at the same time, silver metal is deposited on the copper wire as the silver ions are removed from the solution. Now this is a stylized or diagrammatic form of the typical galvanic cell that produces a specific type or amount of voltage electricity. And this is to show the same type of reaction as we saw in the previous diagram where you have a copper anode, a negative pole, a silver cathode, positive pole, and then you have solutions where copper goes into solution, ions go into solution, silver comes out of solution and deposits it on the cathode, and then a salt bridge is inserted to complete the circuit so that the electricity can flow throughout the cell. The cell potential is this reading up here. Cell potential is created when two dissimilar metals, copper and silver in this instance, are connected and is measured as energy per unit charge available from a redox reaction. A volt is defined as a joule, which is the energy per unit charge, charge being Coulomb. A positive cell potential indicates that a spontaneous reaction will occur and that electrons are flowing from left to right. If you have a negative potential, the reaction is not spontaneous and no flow occurs. This is a standard galvanic cell. The half cells are separated. This is a half cell on this side. This is a half cell on this side. And electrons flow through the wires and can be made you could put a load of some sort, a motor or something in here to be powered by this flow of electricity that occurs. Electrons always flow from the anode, the negative pole, to the positive cathode. The direction of flow is always from negative to positive, from left to right in this diagram. Oxidation occurs at the anode, which is negatively charged. And here is the oxidation reaction. Remember Leo. Lose electrons, oxidized. The copper loses 2 electrons and is oxidized and forms copper ions, which is why this solution turns blue. Copper ions are blue. Reduction occurs at the cathode. Here's the cathode side. It's positively charged. And you remember reduction is gain electrons reduced. The silver ion gains an electron and becomes a silver metal. The cell potential is a result of the inherent differences in the materials that are used. The degree or the size of this number is fundamentally based on what you choose for these two metals. Silver versus copper, zinc versus gold, etc. The salt bridge is present for the specific purpose of allowing for the flow of electrons throughout. Now, in order to designate or show a galvanic cell on a piece of paper, rather than drawing this big picture every time, we have something known as cell notation. Cell notation is a shorthand that provides the information that tells you what the anode is, what the cathode is, and so forth. The active electrode, there are 2 types of electrodes. Active electrodes are when the metal itself that's acting as an electrode is also the material that's undergoing either oxidation or reduction. In this case, it's this magnesium over here. An inert electrode is a cell that does not especially participate in the reduction or oxidation reaction, but acts to facilitate the reaction and keep the circuit closed. In this case, The actual reduction is hydrogen ions to hydrogen gas. Well, since this is not convenient, it's not a metal, you put a platinum electrode in here to facilitate that, and this platinum electrode is what's known as an inert electrode. So we have the oxidation of the magnesium here. It occurs in the beaker on the left. The reduction of hydrogen ions occurs, and it's facilitated by this inert platinum electrode, which allows the electrons to come in and reduce the hydrogen ions. As you can see, here's the overall reaction that occurs. And in cell notation, it's represented this way. I have a mistake here. I should have two lines at this point, which separates the anode from the cathode. So you use vertical lines to show the different species, and then a double vertical line to show the difference between the anode and the cathode. So consider the following redox reaction. 2 chromium solid plus 3 copper ions goes to form 2 chromium ions plus 3 copper solid. Write the oxidation and reduction half reactions and write the reaction using cell notation. Which reaction occurs at the anode and which reaction occurs at the cathode? The oxidation is the loss of electrons by the chromium. So you have 2 Cr goes to form 2 Cr ions plus 6 electrons. The reduction is the conversion of 3 copper ions with the addition of 6 electrons to 3 copper solid atoms. Remember, Leo, you lose electrons. Ger, you gain electrons. In cell notation, it would be written this way. You have the anode on this side and the cathode on this side. And I gave the answer here. The reduction is always the cathode. The oxidation is always the anode. The left side is the anode. The right side is the cathode. Let's look at another example. This is a little more complicated. You have 5 Fe, 5 ferrous ions, plus permanganate, plus hydrogen ions, goes to form 5 ferric ions, plus manganese ions, plus water. So write the oxidation reduction half reactions and write the reaction using cell notation. Which reaction occurs at the anode and which reaction occurs at the cathode? I've already given you the cell notation down here, and because these are all ions and there's no solid, a platinum inert electrode is necessary on both sides. Here you have the anode side and the cathode side. Now let's show that in half reactions. Here's the oxidation reaction. The loss of 5 electrons by these 5 iron atoms or ions to form ferric ions. Then you have the gain of 5 electrons by manganese to form this manganese ion, and in the process water is produced, and so then the overall notation, cell notation, is here. You have oxidation is the anode and is on this side. Reduction is the cathode and is on this side. And you need to show that hydrogen ion participates in this reaction. Okay, so we've looked at the simple oxidation reduction reactions. We've looked at cell notation. So now let's talk about something known as standard reduction potentials. Every element that undergoes oxidation or reduction produces a standard amount of electrical energy. In order to measure that standard potential, however, you have to have a reference space that you declare as your 0 point or your standard point. And the reference is shown in this diagram. The reference is called a standard hydrogen electrode, or SHE, S-H-E. It is the electrode that, by convention, has been assigned the value of 0 and is the reference for all other electrodes. When you look in a table for a standard reduction potential, all the values that you see are based on using the standard hydrogen electrode as the reference or 0 point. And here is the reaction that occurs. You have 1 molar, that's an important consideration, 1 molar hydrogen ions, 2 electrons to form hydrogen gas at 1 atmosphere. Now this 1 atmosphere and this 1 molar are important considerations as the standard 0 point, and this is arbitrarily assigned the value of 0. Hydrogen gas at 1 atmosphere is bubbled through a 1 molar solution of HCl. The platinum inert electrode acts and allows or facilitates the production of this reaction. Electrons, as you can see here, electrons on the surface of this electrode are then available to these hydrogen ions, and they interact to form hydrogen gas, and then the gas bubbles up from the fluid. So, having standardized the hydrogen electrode as 0, all other electrodes can be measured to show what their reduction potential is. Here's an example of copper, which is on the anode side or cathode side. These are all reduction potentials, so they are always reactions that go in this direction, from ion adding 2 electrons to form the atoms. The anode is always the hydrogen electrode. By notation is shown here, and then you measure what the voltage is. And by measuring this voltage, the cell is the cathode minus the anode. This is why the hydrogen is always the anode. It's also because this is called a reduction potential, so that it's always set up so that this is a reducing reaction, and then it produces a certain amount of energy. And so you know this is your cell. You don't know the reduction potential of this, and you have assigned this 0. Therefore, the standard reduction potential for copper reduction is positive plus 0.337. Now, what happens if the reduction potential is negative? Nothing happens. Well, then you measure how much electricity you have to put in order to get this to move, and then that amount of electricity is the reduction potential, and it's expressed as a negative value because the reaction is not spontaneous. And as you look at table 17.2, you'll see that some values are negative and some values are positive, and that's how these values are determined. So a galvanic cell can be used to determine the standard reduction potential for any element. Here we have silver. The again, you put the standard hydrogen electrode on the anode side, you put the silver electrode on the cathode side so that it is being reduced, and then you measure this value. So whatever you see in table 17.2 is for the reduction reaction. If, now this is not in your book, but this is if you reverse the reaction. In other words, if you're in a situation where this is the anode and this is what's happening, then the value just changes its sign from positive to negative. So if you have a standard reduction potential, but you have a material that's being used as an anode, it's being oxidized, then whatever's in the table just changes signs. Okay, so here's a problem we're going to go through. And I'll step through it very slowly so to make sure that you follow what I'm talking about. What is the standard cell potential for a galvanic cell that consists of that's gold, and nickel half cells? Identify the oxidizing and reducing agent, So, we look in table 17.2 and we write both reactions as reductions. So first you have the gold, 3 electrons to form gold atoms. In the table it's plus 1.498 volts. Nickel, plus 2 electrons to form nickel atoms, and it's minus 0.257 volts. Now once you've written these out, you look at these two numbers. Whichever number is larger, if both are positive, whichever number's larger is going to be the reduction side, or the cathode. If one number is negative and the other number is positive, such as in this case, then the positive side is the reduction side. If both numbers are negative, then the one that's least negative is the reduction side, and the one that's most negative is oxidized. And so in this case, because nickel is negative, it will reverse and be oxidized. So the oxidation side is now nickel to nickel ions forming 2 electrons. And notice I changed the sign to positive. The cathode, the reduction side, is the reduction reaction as written above here with plus 1.498. The overall balanced reaction, in order to balance, you have to multiply this top by 3 and the bottom by 2, and you get this to balance out the electrons. And then you write this sum is 1.498 minus a minus this, and it's minus a minus because this is written as an oxidation instead of a reduction, and you end up with 1.755 volts. So the standard reduction potential for this reaction is 1.755 volts. Let's look at another example. What is the standard cell potential for a galvanic cell that consists of magnesium and silver half cells? Again, identify the oxidizing and reducing agent. Again, using table 17.2, you write both reactions as reductions. Here's the first reaction, magnesium gaining 2 electrons to form a magnesium atom. And in the table, it's minus 2.372. Silver gains an electron to form silver atoms. In the table, it's plus 0.8. I think in the table it was plus 0.7996 or something. I just rounded it up to 0.8. Again, looking at these two numbers, this one's negative and this one's positive. So this one remains reduced and becomes the cathode. This reverses and becomes the anode, and you write it this way. Magnesium is oxidized, so magnesium atom gains 2 electrons to form a positive 2.372. The cathode reduction is written just as it's written up here at plus 0.8, and then you balance the reaction. And notice you have to balance 1 versus 2, so you have to multiply the bottom by 2. And notice that the voltages are not multiplied by 2. The voltages remain the same. And you end up with the cell being this subtraction, but because this is oxidized, you minus a minus, and you end up with 3.172 volts. So this would be one of the types of quiz questions that would appear on your quiz, would be to use table 17.2, or I might give you the numbers you need, and using that to find a standard cell potential. Now, let's talk about the Nernst equation. Now, we did not talk about, and I skipped this on purpose, the relationship between free energy and equilibrium constant. There is a significant relationship between free energy and equilibrium constant, as you can imagine. But I decided to skip that because I thought the material was sufficient by itself. These are 3 equations that you'll just have to memorize. We have not used these equations before. This shows the relationship between free energy, the equilibrium constant, and the potential for a cell. And what you can see is you have 3 different equations. This equation relates free energy to equilibrium constant. This is the gas constant, and this is the temperature in Kelvin. This relates the potential of a cell to the equilibrium constant. And again, gas constant, temperature, the number of moles of electrons, and Faraday's constant, which we'll talk about in a second. And then lastly, the relationship between free energy and the potential, cell potential, number of moles of electrons, and Faraday's constant. The new material that's introduced here is known as Faraday's constant. Faraday's constant is the number of moles of electrons, or the charge of a mole of electrons. So you have 6.02 times 10 to the 23rd electrons. Each electron has a charge of 1.6 times 10 to the minus 19 coulombs, and if you multiply that together, you get 9.648 times 10 to the 4th coulombs of charge per mole of electrons. That's why these n's are always the moles of electrons. The Nernst equation is a means of evaluating the cell that's not in standard conditions. Remember, when we were discussing the previous evaluation, the number that we produced was a standard potential, which is right here. The Nernst equation says that the cell potential is equal to the standard potential minus this material right here. This is, remember, what we call the reaction quotient, which was the same as the equilibrium constant, except not at standard or at equilibrium. And so if you assume 25 degrees, that you can take all 4 of these letters and convert it to one number if you assume 25 degrees. These others, and 1 mole of electrons, no, you don't have to do that, I'm sorry. If you assume the gas constant, 25 degrees, and Faraday, you get this number divided by the number of moles of electrons times the natural log of the reaction quotient. And so it's the cell potential is equal to the standard cell potential minus 0.257 divided by the number of moles of electrons times the natural log of the reaction quotient. So let's do a couple problems looking at this. The first one, anytime you know one of the three values that I showed in that initial triangle, that is, if you know the potential, or you know the free energy, or you know the equilibrium constant, if you know one, you can find the other two. And I already showed you in a previous problem that if you're given the reaction, you can, using table 17.2, you can find the standard potential. So let's take that and see if we can calculate all three of these values for this reaction. Well, first of all, you want to write out the two as reductions. Here is this reduction. I'm sorry, this was written as an oxidation, but just to be clear, if you I did that to skip a step and make it easier and fittable on one slide, but you would initially start out by writing this as Fe2 plus 2 electrons is equal to Fe, and get the number out of the back of the book, or out of table 17.2, or in this case appendix L. But I went ahead and reversed it as an oxidation reaction and reversed the sign, and here is, we wrote 2 times that because to balance, but notice that this is not multiplied by 2. And so the cell potential is equal to this number that we've looked at in several slides already, and it's going to be 0.8 minus a minus 4.447, or 1.247 volts. And so that is, this will be the anode, this will be the cathode, and this will be the potential. Now, using the formulas that I've just introduced, first of all, the equilibrium constant, the cell potential, is equal to this combination of numbers times the log of the equilibrium constant. If we assume 25 degrees, which we have here, we can convert all of this into 0.0257 divided by the number of moles. There are 2 moles of electrons, and so you put n is equal to 2 and solve this for k, and you get this huge number here, which means that this is spontaneous to the products, which you could have predicted with a positive voltage that it would be spontaneous to the products. And then using a separate equation, delta G is equal to NFE0, so that N, again, is 2. F is that number I showed you before, 9.649 times 10 to the 4th, and E0 is this number. Multiplying this out, you get 2.406 times 10 to the 6 joules per mole, or minus 240.6 kilojoules per mole. Again, a negative sign for delta G shows that it's spontaneous. If you have difficulty with this, we can talk about this some more in class on Monday. Let's look at another situation, and the question now is this spontaneous? There's a couple ways in which you can determine whether a reaction is spontaneous or not. One way to determine is if it has a positive E0 value, standard potential, it will be spontaneous. The second is if the delta G, as we talked about last week, if the delta G is negative, it will be spontaneous. So there's 2 ways we can determine that. Now notice that we do not have standard concentration conditions. For these to be standard, it has to be 1 molar, so it's not standard. I've gone ahead and written this as a reduction, or an oxidation, and this is the reduction. So I've skipped a step. If you're having trouble with that, we can go over it in class. So that E0 is equal to a minus 447 minus a minus 2.28. So you have a minus 1.173. This tells you that at standard conditions, this is not spontaneous. A negative sign tells you it's not spontaneous. But what about the non-standard conditions? Well, first of all, your reaction quotient, Q, is going to be the concentration of your product, 0.15, divided by the concentration of the reactant. Remember, you don't have to consider the solids. And you get this number, 0.077. You put that in this equation. Remember, at room temperature 25 degrees, the complex number reduces down to 0.0257 divided by N times this, which is, so you take this number right here, that's your standard potential, minus this divided by 2, again 2 moles of electrons, ln, the calculated reaction quotient there, and you get negative 0.014. This is still negative, therefore it is still not spontaneous. Now, we're going to switch gears, and the second part of this lecture is not a bunch of calculations, but just exposing you to some terminology that's used in electrochemistry. And the first terminology has to do with batteries. Batteries are cells that use, electrochemical cells that are used to produce a current that is portable and is a source of electrical power. The diagram on the left here shows the various parts of a fairly standard battery. A primary battery, also known as a dry cell, is a battery that is used one time, and once it's discharged, it cannot be used again, so it cannot be recharged. The diagram here shows the cross-section of a standard flashlight battery, which is a zinc carbon dry cell. Carbon in the middle. Carbon is the reduced agent. It is the anode, and the zinc is on the outside here. It is the cathode. I'm sorry, this is the cathode, this is the anode. The carbon electrode is reduced, therefore it is the anode. The zinc, which is on the outside here, is oxidized, so it's the anode. And this material in the middle is what looks like or acts like a salt bridge between the two. Another type of battery is known as an alkali battery. It's designed because it is more efficient and lasts longer than the previous dry cell. And it is essentially designed in very much the same way. You have the anode connector. There's a powder in here made up of zinc, and then on the outside is magnesium powder with coal. In your book, the reactions that occur in these are shown. I do not require that you know that for this class. Now this is an example of a secondary battery. A secondary battery is a battery that can be recharged. And it is designed in such a way as to allow for the application of electricity to the battery and replenishing of material. And it uses what's known as a jelly roll configuration that allows this to occur. This is a nickel-cadmium battery. This significantly increases the amount of current that the battery can deliver by increasing the various areas of production of electrons. Remember, current is how many electrons are produced. A lithium battery allows the charge to flow within these various pockets of graphite. This is the negative, this is the positive. If you when you discharge, the flow is in this direction. When you charge the battery, it's in this direction. This is the kind of battery that's used in your car. It's called a lead-acid battery. A lead-acid battery consists of 6 cells that are connected in series. So each cell is 2 volts. Connected in series, you sum it up, and it's 12 volts. The battery is used for 2 reasons. First of all, it's used because it doesn't cost a lot. It's made up of materials that are fairly cheap. And secondly, it's used because it puts out a lot of current for fairly small size. And so this high current allows for use in a starter and starting of engines. It's fairly low voltage but high current. The current can be as high as 400 to 500 amps. The other type of cell is known as distinguished from a battery, is known as a fuel cell, and this is a diagram that shows what a fuel cell is. A fuel cell is a device that converts chemical energy into electrical energy, so that's fairly similar to the definition of an electrochemical cell. However, it also requires a source of fuel, and that fuel is commonly hydrogen. And you can see the fuel comes in here, and through the process of electrolysis, it's converted into water. The water is discharged, and then this produces electrical energy by means of this reaction. On the other side is oxygen. So you have hydrogen on this side, oxygen on this side. The value of this is the production, continuous production of electrical power, and all you produce is water. And so the value is that you can produce fairly large amounts of electrical power without a problem of producing a lot of pollution. I mean, all you're producing here is water. The downside is both hydrogen is very flammable and therefore very dangerous, and also if it's in the presence of oxygen, it's even more dangerous, and so the explosive potential of these is fairly high. So this is a schematic of a hydrogen cell, and the oxygen that comes from the air reacts with the hydrogen, and it produces water and electricity. So you're producing water as your only byproduct, and so that is what makes this a very useful material. We're going to finish up talking about corrosion. Corrosion is defined as the degradation of a metal or of metals due to an electrochemical process. Many people don't know this, but when we first received the Statue of Liberty, it looked like this. Notice this is kind of an old picture. There's old boats in the background. And the reason, this is a painting actually, the reason is that the Statue of Liberty, the outer skin was copper. And so it had a copper look about it. But over the years, with the production of corrosion and the elements, the copper has corroded and has produced this, what it calls a patina covering, that's sort of blue-green in color. So it originally looked like this, but ultimately now it looks like this, and that's the process of corrosion. Corrosion occurs, we paint things in order to prevent corrosion. We paint cars, we paint various other things to prevent corrosion. But if the paint loses its continuity, then, and water is present, you can see that you have an oxidation of the oxygen, a reduction an oxidation of the iron, a reduction of the oxygen, formation of iron oxide, and that is what forms here on the anodic site. And this is the process of corrosion. In this case, it's iron material that's being corroded. Iron loses 2 electrons to form iron oxide. This gains electrons to combine with that to form iron oxide. And this is the last slide. This is to show one of the ways that we go about to prevent this from happening. And the process that is used is called cathodic protection. Cathodic protection is you assign one of the 2 materials as a cathode, one of the 2 materials as an anode. The anode is called a sacrificial anode. In this diagram, you have 2 materials that are in the ground. The object that's to be protected, say this is something you buried in the ground to hold fuel oil for your house. And you don't want it to corrode, because if it develops a hole in it, then the fuel oil will leak out. So you bury something else in the ground and you make it of a material that it will function, it will be preferentially oxidized compared to whatever material this is made of. And so this is protected. It's made the cathode. Reduction occurs here. Oxidation occurs here. And then you connect the 2 to complete the circuit. The current, this ground is generally made up of has water that has electrolytes in it, so it acts as a salt bridge, and you complete the circuit this way with a wire in between, and this corrodes and this doesn't, and that's called cathodic protection. One way to protect an underground iron storage tank is through cathodic protection. Using an active metal like zinc or magnesium for the anode effectively makes the storage tank the cathode, protecting it from oxidizing. So that ends our lecture today. Come to class prepared to discuss problems that you're having with any of the problems related to Chapter 17, and we'll spend our time talking about that. I will also be giving you some practice problems to work on in class with your classmates. Thank you.